Hello friends, welcome to my lectures on the topic which is most interesting topic in the 11th standard portion. It's the beginning of a greatest part of mathematics called combinatorics. If you are going to be computer scientist or if you are going to be statisticians and all that, you will come to know how important this particular topic is. And today I have picked up a topic which is fantastic because this particular identity which I had proved last time, that was called Pascal's identity. This Pascal identity has created revolution in the world of mathematics, and it appears at strange places, at various different places. So I want to talk about the wonders of Pascal's identity. Now, before that, although I have already explained this topic in my last lecture, I want to again revise the whole thing. What is Pascal's identity? Pascal's identity can be written like this. I can explain it in a very simple manner. Suppose there are, like this, there are n individuals. There are n individuals, and one of them is, slightly different than others, right? So let us call him like this. So this is a different fellow, right? So there are n individuals here, right? And this one together becomes what? N plus 1 individuals. N plus 1. Now, I want to select R people out of n plus 1, right? I want to select R objects out of n plus 1, R persons out of n plus 1. How many ways that can be done? We all know it is n plus 1 CR, correct? So, I am choosing R objects out of n plus 1. And that number is given by n plus 1 CR. So now this job of selecting R people can be done in two ways. Either you take this special person in the committee, or you don't take, correct? And if I add both the options, I'll get the correct answer. It's obvious because the job can be done either in this manner. That means taking the this special person included and special person excluded. Together, it gives me total answer, okay? So now suppose I want to exclude this fellow, right? Which means I will have to select all R objects from this n only, right? So which means that will be equal to what? nCr, because there are n persons and I am selecting R. How many ways can I do it? nCr ways, very simple, and I am not including this fellow. Now, let us find out. If I include this person, that means I don't have to select now R people. I want to select only R minus 1 persons, right? So it is R minus 1 people are to be selected because 1 is already there in the committee. So now the remaining are R minus 1, and these R minus 1 people are to be selected from this, correct? Because he is already there in the committee. So that means that is nCr minus 1. So very, very simple identity which says that nCr plus nCr minus 1 must be equal to n plus 1 CR. Now this looks like a very innocent kind of identity. What kind of wonders it will have? But let us see if we apply this identity to various numbers, what happens, okay? So let us first of all talk about, let us say, suppose I have 1C0, right? And if I have 1C1, okay? So this is 0 and this is 1, right? So 1C0, apply this, 1C0 plus 1C1, correct? It will be equal to n plus 1 C1, correct? So this will be equal to what? If I add these two, suppose I add these two, right? These two I am adding, okay? So then I will get n plus 1, but n is 1, so here it will be 2C1, correct? Now, that is just a simple application of this, okay? Now, let us put here 2C2 on this side and let us put here 2C0, okay? So now, this is going on. Now, for example, now suppose I add these two. Suppose I add these two and apply this same principle. There R minus 1 is 0 and R is 1, right? Now, if I add these two, then I will get 3C1. Clear? 3C1, right? Plus 3C1. And then if I add these two, then I'll get again 3C2. Correct? As we did in the last time, 3C1, 3C. So here on this side, I will have 3C0. And here on this side, I will have 3C3. Okay. Now, again, I apply the same identity again and again. So now, suppose I add these two. If I add these two, this will add up to what? 3 becomes 4 and R is 1 here. So it will be 4C1. Now, if I add these two, I'll get 4C2. If I add these two, I'll get 4C3. What is left is 4C4. And on this side, 4C0. Now, this is fantastic. Now, if you actually look at these numbers, it will be very interesting. Now, this way I can go on. So, this is called, this kind of building, which is triangular in nature. This is called Pascal's triangle. Pascal's triangle. Now, let us examine what is Pascal triangle in numerical form. This we have done in the form of nCr. Okay, fine. So, now we'll do it by using a numerical form. Okay. Let us see what is 1C0. 1C0 means you are choosing 0 objects out of 1. How many ways it can be done? Only once. Don't select any, right? So, first 1C0 is 1, right? Then 1C1 is also 1, right? Now, if I add these two, I'll get 2. Then I'll add here 2C0 and 2C1, both are 1. Then I add these two, I'll get 3. I'll add these two, I'll get 3. I'll put 1 here and 1 here. Now, if I add these two, I'll get 4. I'll get 6. I'll get 4 and I'll get. Now, again, I'll put 1 here and put 1 here. Then I'll start with 1, add these two, I'll get 5. Add these two, I'll get 10. Add these two, I'll get 10. Add these two, I'll get 5. And then I will put 1. What is this? First of all, you'll be surprised to know that this number is 11, correct? This number is 11 square. This number is 11 cube. This number is 11 raised to 4. This number is 11 raised to 5. Hare? Wonderful, right? Not only that, if you are familiar with the polynomial and expansion formulas, then you will come to know that if I want to expand x plus a, what is x plus a raised to 1? It is nothing but x and a, nothing else. Now, what is the coefficient of this x? 1, right? What is the coefficient of this a? 1. That corresponds to this, okay? Which is very simple. But now, if I write x plus a bracket square, then the expansion is x square plus 2xa plus a square. Now, look at the coefficients here. What is the coefficient of x square? 1. What is the coefficient of xa? 2. What is the coefficient of a square? 1. So, that corresponds to the second line here. Second line, 1, 2, 1, right? Now, not only that, x plus a, let us call cube, right? What is x plus a cube formula? At least this formula you must be knowing from your 10th standard mathematics. So, it starts with x cube plus what? Plus 3x square a plus 3x a square and a cube. This is the formula. Now, look at the coefficients. Coefficient of x cube is 1. Coefficient of x square a is 3. Coefficient of x a square is 3. Coefficient of a cube is 1, which corresponds to the third line here. Now, that is very interesting. So, it always goes without saying that if I want to expand now, x plus a raised to 4, I know the coefficients is already there. The first coefficient is 1, second coefficient is 4, third coefficient is 6, next coefficient is 4, and last coefficient is 1. All I have to do is to supply the powers of x and a. So, that is, it will start from x raised to 4. Then it will continue with x cube into a. Then it will continue with what? X square into a square, right? Then it will become what? X a square and last, x a cube, and last will be a raised to 4. So, this will be x raised to 4, 2, 3, 2 and 1, right? I think this is not quite visible. So I'll remove this and I'll write it again. Okay. Now let us continue with this. So what I want to say is this. Now let us remove all this Pascal's triangle once you have understood the nature of Pascal's triangle. So now let us talk about the fourth power of x plus a. If I want to find out fourth power of x plus a, by now you must have guessed that every term can be written like this. First term is x raised to 4. Okay. Of course, there is a, but a raised to what? 0. So 4 plus 0 is equal to 4. All the time, this total has to be same. The next is what? X cube and a raised to 1. Next term is what? X square into a square. Next term is what? X into a cube. Next term is what? A raised to 4. Correct? Now, these are the terms, but I have written them devoid of coefficients. The coefficients I can find out from here. These are the coefficients. First term has a coefficient 1. Second term has a coefficient what? 4. Here it is 4. Now here it is 6. Here it is again 4. And here it is 1 again. Correct? So I found out the fourth power of x plus a. That means this triangle can lead me to any power of x plus a. X plus a raised to n. Now this particular thing is called binomial theorem. And binomial theorem means what? How to expand x plus a raised to any power. Even if you want to find out 100th power, all you have to do is go through this process. How many times? 100 times. And you will be able to get the coefficients of all these numbers, right? Now, this is a separate topic where we will come again back to binomial theorem. And that is why these numbers are called binomial coefficients. They are called binomial coefficients. Now, what are binomial coefficients? Very simple. You start with nC0, then nC1, then nC2. This goes on till you reach what? nCn. Correct? Now, these are called binomial coefficients, right? And they have got certain properties which are very interesting, which one of them we have already seen here. So, nC1 plus nC2 will be equal to n plus 1 C2, something like that. Okay. So, now one more identity I would like to prove, which is very interesting, and that is this. What is the sum of all binomial coefficients? That is a question. Sum of all binomial coefficients. I'll write it in short. Coefficients means COEFFS, right? So sum of binomial coefficients I want to find out. That is nC0 plus nC1 plus nC2, and this goes on till I reach nCn minus 1, and last will be nCn. And I want to find out what is the total, So actually, if you look at the diagram, you will come to know, 1, 1. This was the first row, right? That the total is what here? 2. Okay. The next total was what? 1, 2, 1. So what is that? That is 4, right? Now 1, 3, 3, 1. What is the total? 3, 3, 6, and this is 2. This is 8. Now what is the next one? 1, 4. This is what? 6. This is what? 4. Then what? 1. What is the total? 1 plus 4, 5. 5 plus 6, 5 plus 6, 11. 11 plus 5, 4 is 15 plus 1, 16. Now, isn't it a coincidence? Now, what is this? This is 2 raised to 1. What is this? This is 2 raised to 2. What is this? This is 2 raised to 3. And what is this? This is 2 raised to 4. Oh, that means this total must be 2 raised to n. Simple. Correct? That is the wonderful identity. So, nC0 plus nC1 plus nC2 is equal to 2 raised to n. Now, you will be wondering why it is 2 raised to n. What 2 has to do with this? Because what is nC0? Look at it like this. There are n objects and I am not selecting any, right? How many ways can I do it? nC0's ways. There are n objects, I am selecting only one. How many ways can I do it? Only one way. How many ways can I do it? Only 2 ways, right? Like this. Now, why this is 2 raised to n? By the way, if there is a set of, say, suppose there is a set A and B, okay? how many subsets it has. Let us see. How many subsets it has? One subset is itself, that is AB itself is the one subset. Then singleton sets kept single A, single B, and empty set. So how many subsets the set containing two element has? 4. So that is 2 square. Now if I take a tripleton set A, B, C, okay, how many subsets it will have? One is singleton A, for is, let us call it phi, okay, empty set. Then singleton B, then singleton C, then AB, right? Then BC, then what? CA, right? So AB, AC, CA, right? And last is what? The ABC, the whole itself, right? So now how many numbers? See, look at 1, 2, 3, 4, 5, 6, 7, and 8. What is this? This is 2 raised to 3. Isn't it interesting? So, and this has got some relation with this because this is also 2 raised. So, total number of subset of a set containing n elements is nothing but 2 raised to n. And why is it so? Because nc0 plus nc1 plus nc2. Because when I select a subset, what am I doing? For example, look at this. Whenever I take set AB, so I am putting a sign of selection on A and sign of selection on B. So I have selected A and selected B. So here I have selected A and B. Now here I have selected A, right, and rejected B. So B cross. Then here I have selected A cross but B tick mark. And here I am putting cross on both. So find out that how many ticks and cross I can make, right? So there are only 2 ways. Either I put a cross or I put tick mark, yes or no, right? That means they are nothing but 2. So there are 2 ways of doing a selecting thing, and therefore it always becomes what? 2 raised to n, you know. So that can be easily understood, that whenever you select a set, whenever suppose I am to select, there is a set called A, B, C, D, and I have selected a subset called A and C. That means I am putting a tick mark on A and C, and I am putting a cross mark on what? C. So how many total subsets will be there? The total number of tick marks that are available. Now total number of tick marks are available are exact. Tick means what? Either 1 or 2. So either it is present or absent, right? So there is only 2 ways. And how many tick marks can I have? Because there are n elements. So every element will have 1 tick mark. So that means it can be either chosen or rejected. So 2 into 2 into 2 into 2 into 2, it becomes 2 raised to n. That is another wonder of this particular triangle. Okay, fine.